So welcome to your fifth lecture in the embedded system course. In the previous lecture, we stopped at the different alternate functions for the different ports and the pins that are on the different ports in the microcontroller. And in the microcontroller that I'm using in throughout my lecture has how many ports? So feel free to pause the video whenever I'm asking questions so you can replicate what happens in the face-to-face lecture and try to answer my questions and reflect upon them. Alright, so in the examples that we've seen in the last lecture, we had 4 different ports, namely A, B, C, and D. And what was so special about port A? So port A was the only port that is physically connected to the ADC, hence it's the only port that could be used for some analog inputs. And the other ports have different functions, alternate functions. Among them, for example, port C has some kind of JTAG interface here. So this is one of the objectives of today's lecture, is to understand the JTAG module, and you've used that particular module in the context of your second tutorial when you programmed the soft microprocessor, which is the NIOS 2. So in your tutorial you created a system with the CPU, which is the NIOS. This is the microprocessor, and then you added some modules to it, such as a clock in order to synchronize everything, some I/O module to control the switchers and the LEDs, some memory for sure in order to be able to store and retrieve data, and finally you use something called the JTAG. So what was the purpose of the JTAG? If you remember quite well, once you've put your system on the FPGA, you still had your computer connected to the FPGA. So your personal computer was still connected to the FPGA. And the idea was to create some software here and make it run on the CPU. And you've seen the results of the compilation. If something's happening wrong on the CPU, on the console on your PC. How that is possible? Well, through the JTAG interface. So the JTAG interface is short for Joint Test Action Group, and this is an interface that we use to test, debug, and program different microcontrollers, processors, FPGAs, ASICs, boards, etc. And the whole idea is to have one single connector on a PC board. So it's connected in a way that we call a daisy chain. So a daisy chain is the daisy flowers when you put them together like that, and sometimes you wear them on your head. And the idea is that the JTAG is a standard, so whether you use it with North American ICs, boards, etc., or Asian ones, it is the same protocol, same standard so they are compatible. Alright, so one of the questions that I asked is to describe this particular schematic. So you can notice that we have an MCU and an FPGA on a board, 2 different modules, and you can notice that there's a way to talk to those different modules, and we try to understand them to guess first their functionality and what is needed in order to be able to test, debug, etc. So first thing that you can notice here, using your experience now with DSD, CA, and now this course, is that we have something called CK. So most probably this feels like a clock. So yeah, correct. This is the input of the clock. This is to make sure that everything is synchronized here. And then you can notice that we have an I and O here. So I/O, usually by your experience, you should know that these are the ins and the outs. So basically this is what we use for the data to get some testing data in, and then the sped out data comes from here. And you can see the daisy chain here, so one after the another, like a cascade. And last but not least, we felt as engineers that something is missing. The thing is, everything is connected with everything, so basically how would we know that we're testing this particular microcontroller and not the FPGA, or vice versa? So basically we need some indicator telling us that we're actually working with the MCU or the FPGA or any other module that could be present on the board as well. So there should be some kind of selection pin, right? And this is the test mode select that enables us to choose between the MCU, the FPGA, or any other module that would be here. One could ask, what happens if, let's say, my MCU is dead? So here the chain is broken, and hence we cannot program or test the FPGA anymore. Alright. We've seen in my example that we have 4 different ports on the microcontroller that I'm talking about. So we have port A, port B, C, and D. And we said that all those ports are bidirectional ins and outs. And so one particular functionality of port 8 when it's not used as a digital bidirectional I/O, so all those are bidirectional digital input-output ports. This one is connected to the ADC, hence it could be used for the analog. Alright, so the idea is to know how to set them up. So we started by trying to find out what information is needed to know how to deal with those ports. Alright, first is the naming convention. So we have X, and X could mean anything. Could mean any of the ports that I presented in my lectures. For the different microcontrollers that you could be using in your tutorials, in your project, or even in your professional life later on, all you have to do is to refer to the datasheet and find out how many ports are available for you to use as inputs, outputs. Alright, so according to the datasheet, we have 3 different registers. One major register, one major thing that you need for to set up your ins and outs is definitely to choose the direction, because remember, they're bidirectional. So this is definitely one needed register, and this register is called the DDR register. So DR feels like direction. Alright, so data direction register. And the X here could be anything, A, B, C, or D. So it could be DDR A for the port A, DDR B for port B, etc., etc. And then we have a register where we write the output data to, and this is what goes outside to outside. Let's say that we're dealing with register C. So we've chosen it as an out port, a particular pin on it. We chose it as an out port, and then the data that we need to send out will be on a particular pin on that port here, using the port C register. Alright, so each port, remember, is made physically out of 8 pins. So physically 8 pins that you can connect, for instance, some LED to them, some push button, some motor, etc., etc. Anything, different things, different modules could be connected to those pins. And for each pin, you should deal with the direction using the DDR register. Should you choose a pin as an output, here you need to say that the value of my output will be written in port. In that case, we're dealing with port C, so it would be in port C. Right? And because we have an output register, we also have an input register as opposed to the output register. Question: how many bits for each register? Answer: we have 8 physical pins here, so we'll be having 8 bits. Each bit represents a physical pin. So if I want my 7th pin here to be an out, so I need to write in my DDR that this 7th pin is an out, and we're gonna see how in the next slide. And then in the port C, number 7 here, we're gonna write 0 or 1, whether if we wanna turn on or turn off a LED, for instance. Alright, so here we're seeing example from which register, from which port. Well, all you have to do is read this screenshot from the datasheet. So here we're talking about DDR-B, so this concerns port B. So the DDR is used in order to choose whether we want it an input or an output. So each pin could be either set up as an in or an out. Alright, now and we can see here the port register for port B and the pin register for port B. Alright? Question: what is that? What is the offset? So if you remember from last time, we talked about different addresses that we can have for the registers, whether they're the general purpose ones or the IO ones, and then of course the memory. So an offset is what allows you to reach one particular register, and this is done by using a base. So if we go with the base 0 here, our register DDR-B is reachable with an offset of 24. So 0 plus 24, it should be somewhere around here. So we can notice that it is an IO register, and it's not a general purpose one. Something you can notice here is from the datasheet again is, and they say that when addressing as IO register now, its offset is 04. How come? So basically when you do that, when you address it as an IO register, your base is not 0 anymore. Your base is the first address that you have in the IO field here, in the IO section here, which is 20. So all you have to do is add 4 to the 20 and you will end up with your absolute address, which is 24. One last thing that you should notice is the reset value. So this is the value upon reset, and you can notice it's all zeros. Why should we have some fixed value here and not a random one? And this is again from last lecture, we need to have a stable state. So it makes sense to have zeros here, so we can know that this is where we starting, and we know what to expect as a behavior. So this is true for the direction register, and we're gonna find out what value exactly means if we're gonna use this particular pin as in or out. But for the time being, let's jump to the port B register, and this is when you write the values you want to send outside inter alia, because it has some other functionality, but for the time being we're gonna focus on that. So it's here when we're gonna put drive 0, 1, 0, 1, whatever, for each of the physical pins that are set up as outputs. And you can see we also have some values upon reset and the fixed ones as well. What else can you notice weird about this particular slide? So basically, it's the same thing when it comes to pin now, and we have the offset value and the relative one, the absolute one and the absolute one and the relative one. But then again, the value upon reset here is x. And you should know that because you've taken the DSD and I've talked about it in the DSD course. So x is not a don't care, it's more a unknown. How come? Well, remember, pin B is the register where you read the incoming data. So here you can never know what kind of data your sensor, let's say, will be spinning out to your microcontroller. So you cannot fix it because it could be anything driven by the sensor. Hence, it's unknown. Alright. So let's see in more details the DDR. So if I'm using the DDR register, I have different pins here. Alright. So X is for the port, and then N is the bit within the register. So for instance, if I want to set up pin number 0 in my port B, well, I'm gonna go ahead and program DDRB0. Alright? So if I want it to be an output pin, all I have to do is write 1 to it. If I want it to be an input, well, I'm gonna write 0 to it. What is the direction by default for the different pins? Well, all I have to do is check the reset value. So upon reset, everything is set up to 0. 0 means they are all input pins. That would sound weird. Why configure everything as input pins? Well, to be honest, it makes more sense to get some data from outside and know how to deal with them in the software, other than spit out some data to outside. And let's say that you're controlling an engine or something like that, and you're forcing everything to 0 or 1. This could be a dangerous situation. So the guys from AVR at Mega decided that they want to make the pins to be by default inputs. Alright, so DDR is for the direction. What are the other two registers? So let's consider that we're dealing with outputs. So the output is concerned with the port register, or the port register is concerned with the output pins. Alright, here we have two different scenarios. The first one is the one that I started talking about, is that I decided that my port B, let's say, is all configured as output. So in the DDR B, I have ones everywhere. So everything is an output. So if I want to drive something, some output module, all I have to do is either write a 1 or a 0. So imagine that I have a LED connected to my pin here, right? So if I want to turn on the LED, all I need to do is write 1 here. If I want to turn it off, all I need to do is write 0. So this is when if I configured my B port as an output port. But I have another option, is in the DDR I could have left it at default with the default value, so with the zeros. So basically I'm having in ports. So port B is all ins. So I'm not going to write any data that is meant to go outside here. I'm writing data that is used for something else. So this is where I ask you, what for? What would I be setting up or controlling here if I'm not sending that data to outside? So if you remember from the previous lecture, we said that we have some pull-up resistors. physically connected to all ports. And in order to use the ports as digital inputs and outputs, we need to activate those pull-up resistors. Hence, if we write 1 to a pin when we're using a whole port as an input, this means that I'm activating the pull-up resistor. Hence, I can use it as a digital input. If I don't activate it, this means that I'm not allowed to use it as a digital input. I can use it for something else. So if I have a 0 or I leave it with the default value, this means that it is tri-stated, high impedance. Right? This could be used for something else. Right? So in order to use a port as a digital input, first off, I need in the DDR register to put zeros, and then in the port register to activate the pull-up resistor, putting ones. If I'm willing to use it as an output, all I have to do is put ones in the DDR and then drive whatever output I need, high or low, using ones and zeros. Alright, so back to the input here. So DDR equals 0, port is equal to 1. I've activated everything correctly. What is still missing? Correct. I need to actually read whatever data is being sent from outside or received from outside. Alright, so all I have to do is use the pin register with a different value. So remember, those are physically connected to the different sensors. All I have to do is go ahead and see what the sensor has written for me in that particular pin. Right? So this could be a push button, for instance. Alright. Let's see an example that would be easier. So, which port is concerned with this particular instruction? So we can see that we have the name A here, so most probably and definitely it's port A. So I'm dealing first with the DDR register. This register is used to do what? To know whether I'm going to use it as an in or as an out. I'm putting all zeros. All zeros means it's the default value, doesn't really matter, but using zeros, this means that the whole port is used as in. If I want it to be an out, well, I need to change the value zeros into 1. So this is a hexadecimal notation here, and this is equivalent to 0, 0, 0, 0. How many bits do we have in total? Correct, 8 bits for 8 physical pins. Perfect. Now I set it up as an input. I want to use it as a digital input. So what should I do next? Correct. Activate the resistors, the pull-up resistors. So in order to do that, I'm going to act on port A. And FF, I'm putting ones everywhere. This means I'm activating all of the resistors of all of the pins. What is lastly should be done here? Now that I set it up as in, so I'm going to read data from outside. Well, I need to actually get the data, and I get it from which register? Correct, the pin register. So I'm using pin A, and I'm putting whatever I read in an intermediate or local variable here. I can then use it in a condition or something like that, etc. Alright, let's see another example. So now I'm using it with register B. What am I doing? Correct, ins as well. And then, whoops, here I did not activate the resistors. Hence, I cannot use it as a digital import. So I'm done. End of the story. Let's see a third example here. Alright, so this is a little bit trickier. What do I have here? 0F. So I'm registered port A, with the direction register. So here, the first half of the pins are considered to be inputs, and the second half are considered to be outputs, because I set them up to ones. So this is output. So I have 4 inputs and 4 outputs for my port A now, thanks to this particular instruction. Now I want to use my inputs as digital digital ones. So what should I do? Unlike here, I need to set up the resistors. So the values for those significant bits here, I need to set them to 1. So this is for my digital input. What about my output? For my output, I want to drive whatever outputs I have, let's say LEDs, I want to turn them off. So I'm going to put zeros everywhere. So what should I do? What would be the instruction? What would the instruction be? Alright, so for the ins it's 1111, so this is an F. And I'm driving low all of my outputs, so this should be a 0. Alright, so on my port A, I'm going to put F0, so F to activate all of the resistors for my inputs, and I'm driving everything, all of the outputs, driving them low to 0. I don't want to drive them low. I want to drive them high. So instead of zeros, I want to put ones. So what should I change in my instruction here? Okay, so instead of having F0, I'll be having FF. Alright, so this is the first and last example in my lectures where I'll be tackling some embedded C. And this is what we usually do when you program in a low level the different registers. So it's all about bit manipulations that we've seen in the earlier example. However, you'll be doing some of that in the tutorials and maybe later on in your projects. It's really up to you. But we're going to see higher level programming in the upcoming lectures. But for the time being, you need to fully understand what's going on in here, so you'll be able to do that on your own later on. Alright, so first thing I'm doing here, I'm creating a main function. So this is where the magic is going to happen. So let's say I want to set up something to an output, a particular pin. Alright, so I've chosen port B. So I need to deal with the direction register in order to set it up as an output, because remember the default value is an input. Alright, so you're all software engineers, so you've dealt with those operations before, those operators before, and we call them bitwise operators. And we do some, we're doing some shifting with that particular bitwise operator here. So what am I doing? I have 1 here and I'm shifting it. How many times am I shifting it? Well, this represents the value 5, and you can guess it from the name because it's the 6th, so it's pin number 5, right, in the B port. And the B port, you have 8 pins, they go from 0 to 7, so this is the 5th one, number 5, right? Okay, so my DDRB with the default value, remember it's all zeros, so this is my D direction register for B. So the default value is zeros here, 0, 0, 0, 0. Right, this is 5 and we have the value 1. So what would be the 8-bit representation of 1? Well, it will be 0, 0, 0, 0, 0, 0, 0, 1. Right? And I'm doing bitwise shifts here 5 times. So the 1 will come from 1, 2, 3, 4, 5. So this is bit number 5, 6 and 7. And this is 0. So my 1 is now here. So I ended up with 0, 0, 0, 0, and here a bunch of zeros, right? So this operation made me have this particular outcome. And then I'm ORing it with whatever value I had in the DDR before. So this is what I'm doing. I'm taking my 1 that I shifted and I'm ORing them together. This means that whatever has been here before, it will be the same. So I'm having zeros here, and the only one that is affected, now I have a 1 here. So I know now that my DDB5 pin is an output, and all of the others, check them out, they are still inputs with the value 0. Perfect. Now I have a perpetual loop, and in embedded systems it's all about perpetual loops, and we're going to talk about those in the upcoming lectures. And check what I'm doing here. It's exactly the same thing. However, same operations, same bitwise operation. However, I'm dealing with pin B7. So B7, remember, the pin is the register where I read data from. This is incoming data. And I'm considering that I've set up correctly the port somewhere, and it's a digital one that I'm reading. Doesn't really matter. What I care about is, as I did for the DDB5, I'm doing for pin B7 here. So it's the last pin in the pin register. So my pin register could be something like, hold on. Yes, could be something like that. X, X, X. So unknown. And I'm shifting, so this is the value 7. I'm shifting my 1 7 times, so it would be here 0, 0, 0, 0, 0, 0, 0, correct? And then I'm ending it with the value that I had from the pin B. So unknown and 0, it would be 0. And then here I would definitely have the unknown. So whatever is driven by the input, right, will affect this particular condition. So if I have a 1 here, if x is equal to 1, the condition will be true. If I have a 0, the condition will be false. Alright. So what I'm doing here now, okay, doing same thing here. So the port B5, remember I set it up as an output. So here I'm shifting the 1 to port B5. So the value of the pin B5 will be 1. Exactly as I did here for the DDB, I'm doing for the port register now. However, what I'm doing is I'm negating. So this is the NOT to whatever result I'm having here. So port B, let's say it's initially, where is it? 0, 0, 0, 0, 0, 0, 0, 0. This is my port B, PB. Alright, now I shifted the 1 5 times. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Voilà. So here I'm having the 1, here I'm having 0, 0, 0, 0, 0, 0, 0. Alright, and this is what I did here. I shifted them and I negate it. So this is the NOT. So instead of having zeros here, well, let me do that. It will be better. So instead of having that, I'm having 1, 1, 0, 1, 1, 1, 1. This is because of the negation here of the NOT. Okay, and then I'm ending whatever I have here to the original value of the port. Alright, so everything will stay the same, but number 5 here, it will be a 0. This means that I'm driving low whatever output is connected to my pin of port B number 5. Right? It could be a LED. This means that I'm turning off the LED. Now I have an else, and I'm doing something else. So what am I doing here? Well, same thing that I did here. I'm shifting the 1 towards P5, so I'll have 1 here and 0s everywhere. And now I'm ORing it with port B. This means that instead of having that, I don't have it anymore. Instead of having that, well, everything will remain the same, but the pin number 5, it will be 1 now. So it's driven high. So the LED is turned on now. Okay? So a real life example would be here. Here I'm using a push button. If pushed, I'm going to turn off the LED, and if left alone, the LED will be turned on. What if I want to do the opposite? What if I'm pushing the button, let's say I want to turn it on, assuming that pushing the button will have 1 here, assuming that, because it's in real life it's not, but it doesn't really matter, it's just an example, right? So all I have to do, if I want to do the opposite, when I have a 1 here, I want to turn on, and when I have a 0, I want to turn off. All I have to do is swap those two instructions here. Alright, this is it when it comes to embedded C. So it's all about manipulating the bits and having different values for the different registers in order to set up something according to the datasheet. And in this case, we've seen it for the I/O modules, so in order to communicate with the outside world. Is this true for the other registers that are inside the microcontroller? Not the general purpose ones, the I/O registers. Is this true as well? Yes, each and every register, each and every feature has a bunch, 1 or more registers that are concerned with that feature, and we need to go and check the data sheet in order to know how to correctly put the 1s and 0s inside them in order to have a particular feature. And this is definitely what you'll be seeing in your next tutorial. You're gonna deal with the ARAF feature. Remember the ARAF? It is the feature that allows you to have more resolution when using a particular sensor. And you're gonna go ahead, and this is a screenshot from the datasheet. You're gonna go ahead and see the register that is concerned with the ARAF in order to program it. And if we check it together right now as an example, we can guess from the naming that there's some ADC, and because it's analog to digital, so basically it is concerned with the sensor, if you remember from 3 lectures ago. So basically these are one of the registers that are used with the ARAF, and you're going to find out that all of those registers are actually used when it comes to the ARAF. Alright, so this is it for today. Take good care of yourselves, and hope to see you soon.